is Professor Paul Munroe. I'm the Deputy Dean of Science at the University of New South Wales, and I'm here to moderate the 2019 Dirac Medal Lecture given by Professor Lene. Before we start, I'm sitting here actually on the UNSW campus today, so I'd like to acknowledge the Vestergaard people, who are the traditional custodians of the land that I'm on today. I'd like to pay my respects to the elders, both past and present, and extend that respect to any Aboriginal or Torres Strait Islanders who are attending the lecture today. We're obviously here for the Dirac Medal Lecture. There will be the opportunity to ask questions at the end of that lecture, and we're going to do that through Slido, which I'm sure everyone's used before. In the web browser, go to Slido, and the code for asking questions is hashtag Dirac2. So you can enter your questions through the lecture, and I'll moderate a question and answer session at the end of that end of the lecture. A little bit of background on the Dirac Medal. It's for the advancement of physics, and it's awarded by the University of New South Wales jointly with the Australian Institute of Physics. And it recognises the occasion of the visit of Professor Paul Dirac to the University of New South Wales in 1975, who gave a series of lectures. They were subsequently published in a book called Directions of Physics, and the royalties from those were used to establish the medal, and that was first awarded in 1979. The past winners of this medal include David Pines, Klaus von Klitzing, Ryan Schmidt, and Roger Penrose. And it's an honour today to introduce Professor Lene Howe, who's going to give today's talk. Before that talk, I'd just like to give a little bit of background to the speaker today. Lene Vestergaard Howe is the Mallinckrodt Professor of Physics and Applied Physics at Harvard University. Prior to joining Harvard in 1999, she was a senior scientist at the Roland Institute for Science in Cambridge, Massachusetts, holds a PhD in physics at the University of Aarhus in Denmark. She led a team who succeeded in slowing a pulse of light to 15 miles per hour and eventually brought that to a stop. They took matters further and they stopped and extinguished a light pulse in one part of space and then retrieved it in a different location. In that process, the light pulse is converted to a perfect matter copy that can be stored, sculpted, and then turned back into light. These results represent the ultimate quantum control of light and matter. Her team also utilised great spatial compression of ultra-slow light pulses to generate quantum shock waves in Bose-Einstein condensates, thereby opening up a new field of studies in nonlinear dynamics of superfluid cold atomic systems. Excuse me. Howe has contributed to a wide range of research fields in theoretical physics and later shifted her attention to experimental and theoretical optical and atomic physics. The research includes studies of ultra-cold atoms as well as channeling high-energy electrons, protons, and positrons through experiments at CERN and Brookhaven National Laboratory. The group has manipulated atomic matter waves with nanoscale structures and performed protein studies at the single molecular level. She is a 2001 MacArthur Fellow and was elected to the American Academy of Arts and Sciences, the Royal Swedish Academy of Sciences, the Royal Danish Academy of Sciences and Letters. She is a Fellow of the American Association for the Advancement of Science and of the American Physical Society. She's also a recipient of numerous awards, including Harvard University's Lede Prize, the Ole Rome Medal awarded by the University of Copenhagen, the Rick Meiter Memorial Lecture Award awarded by the American Association of Physics Teachers. In 2010, she was named World Dane, and in 2012, Thomson Reuters Clarivate Citation Laureate in Physics. In 2018, she was awarded the Lisa Meitner Distinguished Lecture and Medal sponsored by the Swedish Academy of Sciences through its Nobel Committee for Physics, and in 2019 with the Lars Onsager Lecture and Medal by the Norwegian University of Science and Technology. Lene Howe's research is described in Radio Lab's Master of the Universe. So after that introduction, I'll hand over to Lene. After her talk, so there will be questions that you can put in through Slido, and I'll moderate the question and answer session. Thank you.
Well, thank you very much, Paul, for this introduction, and good morning, everybody. I am in Boston in the US, and here it's 5 o'clock in the afternoon, and I can tell you it's totally dark outside. But I'm really honored that I've been invited to give this Dirac lecture. And of course, I would have loved to be in Sydney right now giving the lecture, but it was clear that, because of travel restrictions and they don't seem to be lifting anytime soon, so we decided to go ahead that I give the lecture as this webinar. And I very, very much hope to be able to travel to Sydney and meet with you all once the travel restrictions lift. But for now, I have promised to tell you about, our research on extreme manipulation of light, how we use ultra-cold atoms to slow light down to the speed of a bicycle, and how we can also use these ultra-cold atoms to stop a light pulse and start it up again, and how we can take matters further and stop and extinguish a light pulse in one part of space and then regenerate it in a completely different location. Now, as I indicated, to do these experiments, we need some cold atoms. And when I say cold, I mean really cold, microkelvin to nanokelvin. That's a few millionths to a few billionths of a degree above absolute zero. So as you can imagine, at these freezing cold temperatures, you're not going to get there with your standard household kitchen refrigerator. So we need a special atom cooler. And we have certainly built such an atom cooler. And I show a sketch of it here. In real size, it's about 2 by 3 meters in size. And you see, first of all, there's an atom source. We use sodium atoms for these experiments. And we start out heating this atom source to a high temperature, heat sodium to 350 degrees centigrade. So we get a good vapor pressure of sodium atoms. And thereby we can get a high emission rate of sodium atoms coming out of that source, and we collimate the atoms such that we get out of the source a highly directed, collimated, and intense beam of sodium atoms. Now the problem is, because of the high temperature in the source, the atoms come out with very high temperature, high velocities on the order of 600 meters a second. And that's really too fast that we can efficiently use the atoms. So as soon as the atoms come out of the source, we actually hit them head on with a laser beam. We send a yellow laser beam up through the system, and this laser beam, as I say, will hit the atoms head on just as they come out of the source. And then we use radiation pressure from this laser beam to slow the atoms. Now, the reason that this laser beam is yellow is that it has a color, a wavelength, a frequency that completely matches the characteristic frequency of the sodium atoms. And we talk about that the laser is on resonance with the sodium atoms. Under these circumstances, the atoms will interact very strongly with laser light. So an atom will absorb laser light, and light, in particular laser light, comes in quanta of energy called photons. And an atom, a sodium atom, will absorb a photon, and then photon, well, they carry energy. So the electron in the atom will get excited to a more energetic state. And photons actually also carry momentum. So at the same time, the atom will get a little momentum kick, a little recoil kick in the direction of the photon that is opposite to the velocity of the atom. And then the excited electron will very rapidly fall back down to the lower energy state, and the atom will actually emit radiation, but it'll emit in a random direction. So there's, on average, no net momentum kick from that process. But the atom will keep absorbing light and re-emit in random directions. And each time it goes through that cycle, it'll get a little momentum kick opposite its velocity. So that means that the atoms will decelerate. We will start to slow the atoms down, and it works very efficiently because we are under resonant conditions, as I described. And that means that over just a meter length here, a millisecond of time, that is a thousandth of a second, the atoms will slow from 600 meters per second to 50 meters per second at the end of the slower. And now we can load these atoms very efficiently into a so-called optical molasses created in the middle of an ultra-high vacuum chamber. And the optical molasses is created by 3 pairs of counter-propagating laser beams. There's a beam pair going in and out of the board also. And these laser beams are tuned just slightly below resonance, meaning their frequency is just a little bit lower than that characteristic frequency of the atoms. And what that means is that the laser beams will create this like a viscous medium for the atoms, like a molasses, like a syrup. So the atoms will slow down, their velocities will be damped out in this medium of laser light, and they will quickly cool. And it works very efficiently. So in a matter of just a few seconds, we can load this optical molasses with about 1 billion atoms and cool them to a few microkelvin, that is a few millionths of a degree above absolute zero. Now, I should mention immediately that, the different parts of the experiments, the atom source, the slower, and all the stuff we'll talk more about down here, it's all designed by us and home built. We can't buy this stuff off the shelf anywhere. So a typical day in the lab will look like this. Everybody is busy, designing, building, debugging, and really a small percentage of the time really goes into actual data taking. And let me just introduce you to a couple of the main characters here. We have Naomi Ginsberg, who was a grad student in the lab at that time when the picture was taken. And she's now a professor at Berkeley in the US. And here we have Chris Lowe, and Chris was also a grad student, and he was later one of the few people who started the social media platform Reddit. Now, when we laser cool, this is what it really looks like in the lab. So we have, as you can see here, a big optics table. It's actually a 5 by 16 foot optics table filled to the brim with lasers and optics. And we have these yellow laser beams crisscrossing throughout the laser table. And here you can see a laser beam. This color here is really the color, the frequency of light that matches that characteristic resonance frequency of the sodium atoms. And this is what it looks like in daylight. And you can see there's quite a bit of optics here. There's not a single piece just sitting there for storage. It's all in use when we are running our experiments. And over in the background, to the side of the laser table, you can see the atom slower, and then all the way up in the background, you have the atom source. Let me go closer to that system. And so here's again the atom slower. And down here, we have the main vacuum chamber where the main action takes place. And if we zoom in on that, we can see that up here. And on this main vacuum chamber, there'll be a bunch of vacuum flange windows. We see one here. And when we laser cool, detection is super easy because we can just look through one of these windows and see the cold atoms by eye. Because during the laser cooling process, the atoms will keep absorbing laser light, and then they will re-emit in random directions. They will fluoresce yellow. So the cold atoms look like a little bright sun, yellow, about 1 centimeter in diameter, freely suspended in the middle of the vacuum chamber. But of course, we don't just stand there and look at the atoms. We actually start sending laser beams in through the windows and hit the atoms. And that's what, to manipulate them and make them do what we want. And that's what we use when we create slow light. But we are not quite there yet because, as I mentioned, we really want to get down to nanokelvin, to a few billionths of a degree above absolute zero. And at this point in the cooling process, laser cooling really becomes inefficient. And it really pays to turn the lasers off so there's total darkness in the lab. And then we turn on an electromagnet. It consists of 4 D-shaped magnet pieces. And they are separated here by about 1 inch. That gives you the scale of things. And when we fire this electromagnet up, we fire it up with about 1,000 amperes of current that we turn on in about a millisecond, a thousandth of a second. And then we'll generate a spatially varying magnetic field. That is a magnetic field minimum. And we then use the fact that the atoms are small magnets. They have a magnetic dipole moment. So we can actually trap these atoms in the magnetic field minimum, really trap them basically in a magnetic bowl. And once the atoms are happily trapped, And I show the magnetic trapping potential here, and then we see a bunch of atoms, low energy atoms, high energy atoms, trapped by that magnetic field. And now we can start cooling these atoms by applying a radio frequency field. And if we tune that radio frequency field to a very particular frequency, we can selectively kick out of the trap the most energetic atoms. And then the rest of the trapped atoms will collide and re-equilibrate at a lower temperature. Then we can lower the RF frequency and then kick the next set of atoms out. And then we can keep going. And by controlling the frequency sweep of that radio frequency field, we can control exactly how cold the cloud gets. And if we cool the atoms down to a few nanokelvin, a few billionths of a degree above absolute zero, all the atoms will start piling into the quantum mechanical ground state. That is the lowest possible quantum state, energy state, allowed by quantum mechanics for atoms trapped in this magnetic field. So now with all the atoms in the ground state, they are all in the same quantum state. They are all described by the same quantum mechanical wave function. A physicist would say they are phase locked. More loosely, we could say the atoms move in lockstep. And what we have created here is what is called a Bose-Einstein condensate. And Bose-Einstein condensate is a very strange state of matter. And it's behind the fact that we can have superfluids. And we also have Bose-Einstein condensates when we have superconductors. You know, those kinds of strange conductors that can conduct current with no resistance. And in our lab, in our vacuum chamber here, we also create a Bose-Einstein condensate, in this case of neutral sodium atoms. And you're starting to get the sense here that these experiments, I mean, we are still cooling the atoms. We haven't even started talking about slowing light yet. So you start to get a sense that these experiments, they are pretty long. And when we run for many hours in a stretch. And doing the first slow light experiments, we would typically run, 27 hours nonstop. And during that time, you certainly can get tired. And what you see here is at that time, our new postdoc, Sean Garner, he had just joined us. And as you can see, he wasn't totally up to speed yet. But if you actually manage to stay awake, this is actually kind of the point in the experiments where, you could sort of say that's the most exciting, because now we have a Bose-Einstein condensate trapped by the electromagnet. And the condensate is typically cigar shaped, as you see here. I mean, we can reshape it into whatever form we like. But it's at least when it's created, it first created as a cigar-shaped condensate, and it's has about 5 to 10 million atoms in it, and it's about 0.1 millimeter in size. So quite small, but still, macroscopic. So now what we do is we start hitting this condensate with laser beams, and we start to create some slow light. So now, how do we go about creating slow light? So far I have been focusing on the atoms and how they move around in the trap and how we damp out their motion during the cooling process. Now I'll turn my attention to the internal structure of an atom. And a sodium atom is an alkali atom. It's in group 1 of the periodic table. So what it means is that it has a loosely bound valence electron that's zipping around a central nucleus. And this valence electron can now have very particular energy states, and the energy states this electron can have are dictated, that's dictated by quantum mechanics. And I show these possible energy states for that loosely bound valence electron here. And we see there's a lowest possible energy state. We will call that the 1 state. And in that lowest energy state, that's where we will find all the atoms. All the atoms will have their electron in that lowest energy state when we are done with the cooling process. But we notice that the electron can have a slightly higher energy level. There's a slightly higher energy level or an energy state here. And we'll call that the 2 state. So now with all the atoms in the 1 state, we will shine a laser beam, illuminate the cloud with a laser beam that we call a coupling laser. It's a yellow laser beam. And it has a frequency, we indicated by red here, it has a frequency that matches the energy difference between state 2 and then a much higher energy level up here that we call state 3. So this is a resonant, this is an example of a resonant laser beam, the coupling laser here, and we use that coupling laser to manipulate the optical properties of the atom cloud. And now we will send in a laser pulse or a light pulse. We call that the probe pulse. It's also a yellow pulse, and it's tuned on resonance with the transition that we indicate by blue here. So that means its frequency is a little bit higher. It matches the energy level difference between state 3 up here and state 1 down here. And it's now that probe pulse, that light pulse, that we will slow down. So now let me show you this in a more simplified diagram where I just show the 3 atomic states for the electron. That is state 1, state 2, and the upper energy level, state 3. Those are the 3 states that are coupled by the probe laser field and the coupling laser field. And forget for a moment about the probe laser pulse here and just consider the atom being illuminated by the coupling laser. What that coupling laser will do is it will split this upper energy level here in 2 nearby split levels. And the stronger, the more intense the coupling laser is, the bigger is this splitting. And this is really the name of the game in some sense, because once you can start manipulating the energy levels in the system, you can start manipulating the optical properties of the atom cloud. And when we now send a probe laser field or laser beam into the cloud, and we will typically send it in such that it's resonant, as I said, with this 1,3 resonance frequency here, meaning we tune the frequency smack in between the 2 energy levels. This is a point of high symmetry. But in general, for this laser beam here, the probe laser field, that will see a very strange refractive index profile. That is a very strange profile, a variation of refractive index as a function of its frequency, or its detuning from that resonance frequency between state 3 and 1. And now, if you remember refractive index, glass has a refractive index of 1.5, so it's a little bit higher than the refractive index in vacuum or free space, which has a refractive index for reference of 1. And so when we send light through a window piece of glass, it will actually slow down a little bit by about 30%. So of course, not much to write home about, but still. So now you would say, and I should mention also, refractive index is a reason that lenses work, that eyeglasses work. So now you might say, well, gee, if we want to slow light down, we should create a medium with a very high refractive index. No, not at all the case, because if we did that and we have our atom cloud and we send a light pulse in towards that atom cloud, the atom cloud would just act as the world's best mirror and reflect the light right back in our face. So rather what we do is we maintain a refractive index that's very close to 1, but then we generate a very steep slope, a very rapid variation of that refractive index as a function of frequency around the 1,3 resonance frequency. And it's now that steep slope that we use to slow light, because if we send a light pulse in, that light pulse will, have a finite duration. It might be a few microseconds long. And that means that it doesn't have a totally well-defined frequency. There's a little bit of frequency smearing. So the light pulse can actually sniff out this steep slope. So the speed of the light pulse will then end up being inversely proportional to that slope. So this is the pulse velocity, the signal velocity, or group velocity of a light pulse. And the idea is now that we can control the slope of this refractive index profile by just controlling the distance between the energy levels here. And we control that with the intensity of the coupling laser. So if we use very low coupling laser intensities, we can get these energy levels very close together and then generate a really steep slope of this refractive index profile and thereby generate really slow light. And as a matter of fact, the light speed is directly proportional to the intensity of the coupling laser. So it's very easy to control the light speed. But I should mention something else, which is transmission. well, how about the transmission of these light pulses through our atom cloud? And you should realize that there could be problems here, because under normal circumstances, if we didn't have the coupling laser present and we tried to send this light pulse into the atom cloud, this is a light pulse that is on resonance, and we send it into a cold atom cloud, this light pulse would be completely absorbed. There would be no light coming through on the other side. But by first illuminating with a coupling laser and then sending the light pulse in, we can generate a narrow transmission window around resonance for this light pulse. So we can actually get, when the light pulse is resonant, we can actually get light through this atom cloud. So it's like getting light through a wall. And this effect is an effect called electromagnetically induced transparency. And both the fact that we can get transmission through the cloud and the fact that we can generate and maintain very steep slopes of refractive index in our system, even when we have damping in the system, both are due to that we are playing with quantum mechanics. They're really both due to that we generate a destructive quantum interference in the system. And how that works is most easily seen for the transmission case. So let me go through that, because now we can ask, what is transmission, or equivalently, what is absorption? So if an atom absorbs a probe laser photon, it will get excited from state 1 to state 3. But now we can see the system has another path to the same final state. The atom could also start out in state 2, absorb a coupling laser photon, and end up in state 3. And now quantum mechanics tells us that if we have two paths to the same final state, we should associate with each path a probability amplitude that is a complex number. And to figure out what is the probability that the system will end up in state 3, we simply have to add these two complex numbers, take the absolute values and square that to get the probability. But now the thing is that complex numbers can in particular be negative. So if we play our cards right, we can actually get these two paths to exactly cancel, such that we have no absorption from either laser beam. And what does it mean to play our cards right? It means that we, and this again, we are playing with quantum mechanics, we don't want the atom to be in just 1 or just 2. We really want the atom to be in both 1 and 2 at the same time. So we talk about that the laser beams bring the atom into a superposition state of state 1 and 2. And that superposition state is such that we have just the right amount of the atom in state 2 relative to state 1. And it's such that the probability amplitude for finding the atom in state 2 relative to state 1 is proportional to minus, and of course the minus is important, times the ratio of the electric field amplitude of the probe laser field relative to the coupling laser field. So now when we have this magic superposition state, we will get that cancellation of the absorption from the two laser fields. As I said, such there's no absorption from either laser field. So the atom is kind of in the dark. It doesn't see the laser field essentially. So we talk about this magic superposition state as a dark state. And we can see how the light fields, it's really the light fields bringing the atom into that dark state. And we can see how the light fields will start writing themselves into the atomic states. And this whole idea of dark states is very important for everything I'll be talking about. But at this point, let's say enough about theory. Let's get to the experiments. So what I show you here is a setup, and we can run it with different geometries, but this is really the setup we used for the first slow light experiments. So you're sort of familiar with the features of the experimental setup. We have a cutout here of our vacuum chamber. We have the condensate in the middle of the vacuum chamber trapped by the electromagnet. And then we illuminate from the side, in this case with a coupling laser. And then we send a light pulse in along the long dimension of the atom cloud. And now to measure the light speed, we simply sit and wait behind the vacuum chamber for this light pulse to come out. And we measure the arrival time with a light detector, a photomultiplier. And of course, to figure out what the light speed is, we also need to know how long this cloud is. So to figure that out, after the light pulse has propagated through the system, we send a third laser beam in from down below. And now the absorption, the atoms will create an absorption shadow in that laser beam. and we can now image that absorption shadow with lenses onto a camera, and we simply take a snapshot of the atom cloud. And I show you an example up here where we have taken a snapshot of a cloud that we have cooled to half a microkelvin. That's half a millionth of a degree above absolute zero. And in this case, it's clearly a cigar-shaped cloud, and it's 0.2 millimeters in size. So now I will show you what happens when we send the light pulse into exactly this cloud. So we'll see light detector signal as a function of time in microseconds. A microsecond is a millionth of a second. So we first record with no atoms in the system, we record the blue pulse, which is a reference pulse just to set the zero axis or the 0 point for the time axis. And then immediately after, we let atoms into the system, cool them down, and then we launch another light pulse. And now we get the red light pulse out. And as you can see, this light pulse is slowed by 7 microseconds in a cloud that's only 0.2 millimeter long. So now you just divide these two numbers out, and you immediately get a light speed of 32 meters per second. And you should compare that to the normal light speed, that's like 300,000 kilometers per second. So we have just slowed light by a factor of 10 million. And now if you lower the intensity of the coupling laser beam and propagate through a basically pure Bose-Einstein condensate, you can get the light speed down to just a few meters per second. And at that point, you can definitely beat light on your bicycle. So what I will show you now is what it feels like to be a light pulse in one of our cold atom clouds. So I will show you an animation here where we have the condensate, we illuminate from the side with a coupling laser, and then we have a light pulse here that I'll send into the atom cloud, and then for comparison, we have a reference pulse running in vacuum. So then let me get rid of the laser pointer here. So let me launch this. And let me stop it here temporarily. Now we can see what happens is that the light pulse enters the atom cloud. The front edge will slow down, but the back edge is still out in free space. So that's running at the normal light speed. So the back edge will start to catch up to the front edge, and we'll start to get spatial pulse compression. And now as we continue, the pulse spatially compresses by the same factor as it slows down for this animation by a factor of 2.5. And we can see the reference pulse is definitely winning the race. And now the light pulse starts to exit. The front edge speeds back up to the normal light speed. So the light pulse stretches back out, and it ends up with the same length it had before it entered the cloud. It's just enormously delayed. Let me show you an example that is a little closer to the experimental parameters we are running at. So this is for light speed reduction of a factor of 10. So we have the pulse compressing, slowing down, and chucking along. The reference pulse is long gone, and then stretching out again. And let me just run it once more. And then stop it right here. So now, of course, in our experiments, we're not talking about a light speed reduction of a factor of 10. We are talking about factors of tens of millions. So that means that the light pulse from being 1 kilometer long, roughly, before it enters the atom cloud, compresses to being only 0.02 millimeters. So less than half the thickness of a hair. So even though our condensates are small, the light pulse ends up being even smaller, so it fits snugly inside the atom cloud. And the light pulse will now, as kind of indicated here on the animation, light pulse will actually create an imprint in the atom cloud, kind of like a little holographic imprint. And that happens via this dark state formation, because inside the localized light pulse region, the atoms are in these dark states, and there's a spatial modulation of the dark states in the middle of the light pulse where the electric field amplitude of the probe pulse is high. A lot of the atoms have been transferred from their initial 1 state to the 2 state. On the fringes of the light pulse, where we have weak electric field amplitude, only a little bit of the atoms are transferred to the 2 state, and outside the light pulse, the atoms are in their original 1 state. And this little imprint follows along with the light pulse as it slowly propagates through the atom cloud. Now you could ask, could we possibly stop light in the lab just as I did here on the computer? And the answer to that is yes, and it's just as easy. And that's what the data here show. We have, first of all, up here in this figure, we have a pulse delay measurement of the type I have shown you before. We have the reference pulse, and then the delayed pulse that has been through the atoms. And what I also show is what the coupling laser is doing, its intensity as a function of time. So we can see that we turn it on just a few microseconds before we send the light pulse into the system. Now down here we do something different because at the point in time when this light pulse has slowed, is compressed, is contained within the atom cloud, we abruptly block the coupling laser, we turn it off, and you can see there's no light pulse coming out, it's missing. And then we leave the coupling laser off, and when we feel like, in this case, after 53 microseconds, we turn the coupling laser back on, and out comes the light pulse. We can see exactly the same intensity, shape, everything as we had before. So clearly in this case, we have stopped the light pulse. Down here, we do the same thing, but note the break in the time axis. In this case, we stop the light pulse for close to a millisecond. This is a thousandth of a second. During that time, light would, under normal circumstances, travel through 300 kilometers of free space. Now, what's happening here is when we turn the coupling laser off, the light pulse actually comes to a grinding halt and it turns itself off. But the information that was in the light pulse is not lost because that was already imprinted in the atoms through that holographic dark state imprint. So when we later turn the coupling laser back on, the system has all the information to regenerate the light pulse, and we regenerate it and it moves on as if nothing had happened. Now we can play with this system, and let me just show you an example here. Rather than just turning the coupling laser off and back on, we can turn it on and off a couple of times. So thereby we can send a single light pulse into the system and store it, and then we can regenerate it in 2 small pieces, and down here even in 3 small pieces. So it shows you the kind of control we have of this system. And this system can clearly be used for memory buffers for optical information, and it can be used for both classical optical pulses and for quantum pulses of light. That is, for example, pulses of light that have just a single photon. And these memory buffers can be used, for example, in applications for quantum computing. And they have, a lot of people have been using these results for creating or using the system for quantum memory, for storing quantum states of light. And again, in connection with quantum information processing, quantum computing applications. But here I don't want to dwell on that. I want to kind of keep moving. And so let's sort of remind ourselves the process we have just been talking about. So we have the condensate, we illuminate it from the side with a coupling laser, and then we send a light pulse in, we slow it, compress it, we stop it, we extinguish it, we create our dark state imprint. And now this dark state imprint, that means that the atoms end up in a superposition of state 1 and 2. So we really create an imprint of state 2 atoms. And how does the atom, or at least part of the atom, get into state 2? Well, for an atom to get from state 1 to state 2, it has to absorb a probe laser photon, and then it's stimulated to emit a coupling laser photon. So it's a 2-photon process. And since each photon carries momentum, the part of the atom that's in state 2 will get a momentum recoil from 2 photons. And in this case, where the coupling and probe lasers are perpendicular to each other, that momentum recoil will be at 45 degrees. So we should actually see the state 2 imprint being kicked out of the condensate at a 45-degree kick-out angle like this. So let's go into the lab and check if our understanding of this process is correct. Are they being kicked out at a 45-degree angle? And are they being kicked out at all? What happens? So we go into the lab, we start out by taking a picture of the initial condensate of state 1 atoms, and then we illuminate it from the side with a coupling laser. And then we come in with 2 probe laser pulses, in this case, just to be fancy. We come in with one from the bottom and then one from the top. we slow and compress both of these light pulses, we stop them, extinguish them, and we create the state 2 imprints. And now we then want to figure out what happens to these state 2 imprints. So we retune our imaging laser, we change the frequency, so we'll selectively image the state 2 atoms. And let me show you what we see as a function of time after we create these imprints in the lab. So here we go. So now you can clearly see imprints being kicked out. These are atoms, real atoms flying in the lab. And we are starting to run out of field of view on the camera. So let me put these images on a single figure. And you see here that we have the initial condensate of state 1 atoms, and then you have these state 2 imprints as a function of time. And we can clearly see that these state 2 imprints are being kicked out at 45-degree kick-out angles. And I should mention that these state 2 imprints, they're actually themselves little condensates, but condensates of a different nature. They're condensates of state 2 atoms being emitted from an initial condensate of state 1 atoms. And you might now ask, gee, what would happen if I create a second condensate of state 1 atoms and let these imprints of state 2 atoms fly into that condensate? What would happen? Well, we decided to go into the lab to check that out. And so in this case, what we created was not one condensate of state 1 atom initially, but 2 condensates of state 1 atoms. And I should stress that these 2 condensates of state 1 atoms, they are created completely independently. They have never seen each other. They are completely separate and independently created. And what we'll then do is we'll send the coupling laser in from the right, and then we'll send the light pulse into the left, the first condensate here, the left condensate, and then stop and extinguish that light pulse. So this will look like in this animation here. Let me just get rid of my laser pointer. So we come in with a coupling laser and then the light pulse in, and we slow, compress, stop and extinguish that light pulse, and we are left with a state 2 imprint. And now, because the probe and coupling lasers are counter-propagating, this state 2 imprint will get a 2-photon momentum recoil, so it'll actually start moving. And it will it will start moving, and it will actually move out in free space, exit the condensate and move out in free space, as I showed here in the animation. That's what we expect. So let's then go to the lab and check that out. So we have the 2 condensates of state 1 atoms that we start out with before we start bringing light in. And then we illuminate from the right with a coupling laser, and then we send a light pulse into the left condensate here, stop it and extinguish it. And then we just wait. And after we wait 1.3 millisecond, that is 1.3 thousandths of a second, we take another photograph, and now we can see out here, we have something extra. What we have out here, what we are imaging, is indeed a state 2 imprint. So what we have now created here is a perfect matter copy, a copy in matter form of the light pulse we have just extinguished in the first condensate. And if I claim it's a matter copy, that it's a perfect copy of the light pulse, you might ask, why is it boomerang shaped? Well, the reason is, if you think about it, when the light pulse is slowing down in the condensate, it will slow down. We illuminate the whole condensate with light. It will slow down most along the center line of the condensate, where the density of atoms is the highest. And it will slow down much less on the fringes of the condensate, where the density is much, much smaller. So the light pulse, as it's propagating through the atom cloud, will actually itself develop a boomerang shape. And that boomerang shape of the light pulse is perfectly mimicked by the shape of the matter copy. And now, as time goes by, we will eventually see the matter copy moving on and reach the second condensate of state 1 atoms, And if we don't do anything, the condensate will come out on the other side. We can see it on the other side here. But now, on the other hand, if once the matter copy is embedded in the second condensate, if we then re-illuminate with a coupling laser, lo and behold, out comes the light pulse. So in this case, what we have done is we have stopped and extinguished the light pulse in the first condensate and regenerated it in the second condensate. So here's the whole process. Coupling laser in, and then light pulse sent into the first condensate, where it's turned into a matter copy that travels across to the second condensate, and it's converted back to light, and off it goes. Now, if you start to think about that process, the more you think about it, the more weird it actually is. Because you might ask, here we have a matter copy that's generated in the first condensate. How on earth can that matter copy, together with the second condensate, figure out to regenerate the light pulse? The trick we are using is that we are using a Bose-Einstein condensate. So what happens is that when we illuminate with a coupling laser field, the atoms in the state 2 imprint, the electrons in these state 2 atoms, we will dither these electrons due to the coupling laser field. And these dithering electrons, these oscillating electrons, will emit light. But all the atoms under normal circumstances, they would just do their own thing. So all these little oscillators, that they would just oscillate, at whatever random phase relative to each other. So they would each do their own thing and create some randomly scattered light or emitted light. So the light we would be getting out would just be coming out in random directions and have no information content. But in the presence of the condensate, these oscillators will actually phase lock. So they will all, and this has to do with this lockstep nature of the condensate. That lockstep nature of the condensate will force these oscillators to oscillate in phase. So they will phase lock the oscillators. So now they can cooperate to regenerate the light pulse, so we can get the information back out in the light field and generate the light pulse. Okay, so now when you have light in matter form, it's easy to manipulate. So you could grab onto this matter copy here, for example, with a focused laser beam, sometimes called an optical tweezer, just as an example. And then you could almost literally put it on the shelf. And then when you feel like it, you could bring this matter copy into overlap with either the second condensate or the first condensate or just some other condensate you make. If you do that, you can regenerate the light pulse. But now, while you're holding onto the matter copy, you can also start to sculpt it. You could change its shape, for example. So you could really change the information content of that light pulse. And whatever changes you make to the matter copy will be in the light field when you regenerate the light pulse. So that means now that we can start using our system here, not just as memory buffers for optical information. We can also use this system to process optical information. And that can be used, for example, for quantum computing. And as many of you might know, there's a lot of work going on in the world trying to make quantum computers. And the quantum computer is this new powerful type of computer that can solve hard problems that it's not possible to solve on classical computers, the kind of computers we know of today. But of course, the amount of processing we'll be able to do with the system will depend heavily on the kind of processing time we have available. And that means how long can we hold on to this imprint? And in the first experiments here, we are holding on to it for milliseconds. That's a few thousandths of a second. But by manipulating our system, for example, with magnetic fields, we have gotten we can hold on to the imprint all the way up to a full second. And we have actually taken matters further and developed other new tools so we can hold on to the imprint for half a minute. And now you might say, why stop with one light pulse? Why not send 2 light pulses in and create 2 matter imprints? Or why not send a whole 3-dimensional pattern of light pulses in and then store these light pulses as, in highly compressed form as a 3-dimensional pattern of matter copies. And then you could let these matter copies interact during the storage time. And then once you're done with the processing, you can read out these matter copies back out to the light field. So let me take as an example the case of the 2 pulses. I mean, we have developed tools so we can actually, so we should be able to do precisely what I'm describing here with multiple pulses. And let's take the example with 2 pulses. So you could send 2 pulses into the system, 2 light pulses, turn them into 2 matter copies. And now you could take these matter copies and bring them together and let them interact. Now, the thing with light pulses is that light doesn't interact with each other, but matter, once you have light in matter form, you can get very strong interactions. So then you let these matter copies interact for a while, and then you take them apart. And now you can read each matter copy back out to the light field. And the thing is that the information content of one light pulse will be heavily dependent on what was in the other light pulse and the other matter copy. So this is a concept called conditional processing, and a very important concept for quantum computing, for example. And to just illustrate what I was just saying, let me show you an animation here so you have a better idea of what I was talking about. So we have the condensate, and then we can send the first light pulse in. So here it comes, and then we turn it into a matter copy. And now we can use magnetic field gradients to place it where we want it. So maybe off to the side here, so that's a good location. And then we can send the second light pulse in, turn that into a matter copy. And now we can move the 2 independently of one another. We can bring them close together, make them interact, and then take them apart. And then we can turn one matter copy into a light pulse again, and convert the second matter copy to light. So that's the kind of toolbox we have developed that we would be able to start doing these kinds of processing with our system. And now you could imagine, I mean, we love to imprint information in light and send it around in optical fibers. You do that all the time when you're on the internet. Most likely the information you download from the internet has come from some server to your computer via optical signals in optical fibers. So now imagine you take a system like ours and place it in a node of the optical fiber network. You could now have light pulses coming in, you turn them into matter copies, and then you let them interact. And then once you are done with the processing, you turn them back to light and then send the light pulses down other optical fibers. So that's some of the possibilities we have with this system. But I think I'm about out of time here, so I want to be sure we have time for questions. So let me just show you the grad students and postdocs who have worked very hard on the projects I've been telling you about. I have already introduced you to Naomi Ginsberg and Chris Lowe. Let me also mention here Zachary Dotson in the background. In the costume, he was very instrumental in doing our first slow light experiments. And I should point out also postdoc Wei Zhang and grad student Evan Walsh. They were instrumental in developing the long storage times for the matter imprints. And then I should mention that Jessica Krosnow here made the animation I showed at the end. And I want to, of course, thank our great sponsors who have sponsored the research. And with that, I will open the floor for questions. Thank you very much.
Thank you, Lene. So normally I think I'd be leading applause for a talk like that, which I'm probably actually going to do virtually. I'll just see what the questions are. So just to remind anyone, if you have questions, put them through on Slido, and the code for that is Dirac 2. While I'm asking the first question, if you do have a question, if you could quickly type that in, I'll be able to ask Lene that. So the first question, for the optical memory, what determines how long the memories last? Is there a fundamental limit on that time?
It's basically the fundamental limit. In some sense, there's not a fundamental limit. What limits a lifetime in practice is collisions between, typically between the imprint and condensate atoms. And that can lead to that perhaps that the atoms, they collide, and they might change their internal state, or they might get kicked out of the condensate. So these inelastic collisions can lead to losses. So the losses come from collisions, but you can actually, by applying magnetic fields, you can actually apply magnetic fields or magnetic field gradients, for example, to pull the imprint out of the atom cloud. And I can actually show you that, what that looks like. So we have data that I didn't go through, but let me just show you this slide. So what we see here is where we have actually, we have the condensate of state 1 atoms, and let me get the laser pointer again. So we have the condensate of state 1 atoms, and we have created an imprint of state 2 atoms. And with a magnetic gradient, we have pulled it completely out away from the host condensate. So we can now store that imprint completely separate from anything else. So we avoid these deadly collisions that will limit the lifetime. And then once we are ready to revive the light pulse, we just bring that imprint back into overlap with the state 1 condensate. And then we can, we turn the coupling laser on and regenerate the light pulse and convert the state 2 atoms to state 1 atoms, and out comes the light pulse. So it's really from collisions that we can minimize. And then ultimately, when we separate them, like I'm showing here, you can have collisions still between atoms. And if you have 3-body collisions, that will ultimately lead to sodium dimers, because ultimately you could say sodium at very low temperature is actually a solid in equilibrium. So ultimately you would if you waited long enough, you would turn it into a sodium droplet. But you can again control that by increase, just lowering, putting it into an optical trap, where you lower, during the storage time, you lower the density, change the shape, lower the density of the imprint, such that you will minimize collisions. And then when you're ready, if you feel like it, you can then tighten the trap again and make it smaller for readout. So there's a lot of tricks you can play in terms of manipulating these imprints to really minimize losses. But again, collisions are what limits the lifetimes in reality.
Okay, thank you. Excuse me. The next question is, what fraction of the initial cooled atoms end up in the Bose-Einstein condensate?
Yeah, so we start out with about 1 billion atoms when we start the evaporative cooling process. When we are done with laser cooling, we have about 1 billion atoms. So that's 10 to the 9 atoms. And then we once we go through that evaporative cooling process, where we keep kicking out the hottest atoms in the sample, we end up with about 10 million atoms. So that's about 1% of the atoms that end up after the evaporative cooling process and actually in the condensate.
Okay,
so
one more question. In the initial slow light experiment, what is actually moving in the atom cloud? Was the light going through the atoms, or certain atoms moving through the cloud?
It's actually light going through the atom cloud.
Okay.
Yes, it's absolutely light going through the atom cloud. There's a little highly compressed light pulse in there that's moving slowly.
Thank you. Excuse me. What proportion of atoms in the Bose-Einstein condensate are getting imprinted, and can you saturate that?
Yes, you could potentially. So basically, and that's one of the nifty features, and also why that state 2 imprint is truly a perfect copy of the light pulse. In the matter imprint of state 2 atoms, you will find as many 2 atoms as you had photons in your light pulse. And sort of for typical light pulses I have shown here, you might have 50,000 photons in your light pulse, and that means that there will be 50,000 atoms in your state 2 imprint out of the 10 million atoms you had originally in the condensate. And also the interesting thing is, if there's a quantum uncertainty in quantum fluctuation or quantum uncertainty in the number of photons in your light pulse, that same quantum uncertainty will be in the number of atoms in your imprint. And then, of course, if you then start taking a photograph of the imprint, you are actually making a measurement on the imprint and thereby forcing the atom, the state 2 imprint, to make a decision. How many atoms do I actually have? So you collapse the wave function. But of course, if you want to preserve your quantum state, matching the quantum state of the light pulse that came in, just don't do a measurement on it. Let it propagate to the second condensate and then store it or regenerate it. But it really has that same quantum feature, and it also works if you use the system for light pulses that have, at the single photon level.
Right, thank you. I'm a little bit conscious of time. We're a little bit over time, so we'll hold the questions there. I would like to thank all the people who are attending this lecture, wherever you may be and whatever time zone you're in, for sitting through a really fascinating lecture. It's probably the only non-physicist in the room and someone who this information is completely new to. I absolutely found it fascinating, that the ability to control and manipulate and sculpt light. It was something obviously I wasn't aware of, and just found it utterly fascinating that you've been able to control light in such a precise way. So for me, it was a revelationary hour. So normally I would lead an audience for a generous round of applause. I will do that on my own, but thank you so much for presenting today. I hope everyone in the audience got as much out of it as I did, because I thought it was just an amazing revelationary talk to me. So thank you very much.
Thank you very much.
Thank you.